Deep space appears entirely empty, yet this void contains a measurable energy density known as the cosmological constant. This comparison reveals the anomaly. The energy density we observe is 10 to the negative 29th grams per cubic centimeter. Current theory predicts a value, the Planck density, that is 120 orders of magnitude larger. Physicists have struggled to explain this discrepancy. No standard model has successfully proven why vacuum energy isn't exactly zero, or why it isn't massive enough to prevent the universe from expanding at all. Resolving this fine-tuning problem requires reconsidering the cosmological principle, the assumption that the universe remains locally uniform across all scales. Cosmic inflation is the established mechanism used to describe how the early universe smoothed itself out, solving the flatness problem. This exponential stretching creates a local region of space so vast that it appears perfectly uniform to any observer inside it. But when the mathematics of chaotic inflation are pushed to their limit, the process results in a self-reproducing fractal multiverse. In this framework, the multiverse emerges as a direct mathematical consequence of how the early universe expanded. The process begins with a slow-rolling scalar field, denoted as phi, resting on a potential energy curve. Classical physics dictates its movement. 3h phi dot equals negative v prime. This field slides down the potential energy curve toward a minimum. We can measure this descent. Every Hubble time, the field decreases by a specific amount, delta phi. If this classical roll were the only mechanism at play, inflation would end at the same time everywhere, resulting in a single uniform universe. However, in an expanding space, the field is also subject to constant quantum fluctuations. Because space is stretching so quickly, these fluctuations freeze at a specific amplitude. Lowercase delta phi is approximately Hubble over 2 pi. This creates a competition between the steady downward pull of delta phi and the randomized up and down jumps of quantum fluctuations. At high enough energies, the amplitude of the quantum jumps becomes significantly larger than the classical downward roll. In these regions, the quantum jumps up the potential curve counteract the classical downward trajectory. This breaks the uniformity of the early universe, as different regions of space are pushed toward radically different energy values. To understand the result, we have to look at the three-dimensional expansion of space itself. Every Hubble time, the total volume of space expands by a factor of e cubed. In the specific regions where the scalar field jumped up the energy curve, the rate of expansion increases. These high-energy regions expand exponentially faster than their surroundings, quickly coming to occupy the vast majority of the universe's total volume. This creates an eternally growing fractal of disconnected pocket universes. But while eternal inflation provides infinite volume, it does not explain why the physical laws inside our specific pocket universe allow for life. The variation in those laws is explained by the string theory landscape. While vacuum stabilization was once a problem, frameworks like the KKKLT construction showed that string theory supports a massive number of metastable states. This topographic map shows the scale. There are 10 to the 500 possible vacuum states, each with its own unique set of physical constants. Regions can move between these states through quantum tunneling, phasing through energy barriers into adjacent valleys. Because the energy barriers are positive, the time required for this tunneling is always finite. Combined with eternal inflation, this means the universe has infinite time to sample every possible state in the landscape. This ensures the multiverse naturally creates regions representing every possible vacuum energy value and fundamental constant allowed by physics. We can now unify the volumetric expansion of inflation with the vacuum tunneling of string theory. This is Linday's visualization of a chaotic, self-reproducing inflationary universe. The distinct colors represent different vacuum states sampled from the landscape. The narrow tubes connecting these bubbles represent bottlenecks, where quantum jumps and phase transitions alter the laws of physics in the offspring. In this model, inflation generates infinite volume, while the landscape provides the variation required to sample every possible physical configuration. This fractal reality addresses the cosmological constant anomaly. If we apply the anthropic principle to the 10 to the 500 possible states, the fine-tuning of our universe becomes a statistical necessity. In a multiverse with 10 to the 500 tries, Even a 1 in 10 to the 120 event is certain to happen somewhere. We exist in a low-energy pocket because those are the only regions where galaxies can form and support observers. But how do we validate a theory if these other pocket universes exist beyond our horizon? We look for the polarization pattern left on the cosmic microwave background. Detecting these pinwheels would provide direct evidence for the inflationary mechanics that drive the multiverse. Additionally, particle detectors searching for extra dimensions could validate the string theory assumptions underpinning the landscape. While we cannot see the other bubbles, validating the mechanics of inflation and string theory proves that our universe is a tiny, probabilistically selected pocket of an infinite fractal reality.